Hi, everybody. So this is the answer or the solution set to the homework set I gave you on Friday in preparation for the test that we're going to have on Thursday. So let's just get right into it. The Grand Canyon at its deepest point is 1,600 meters deep. If I were to drop a rock into the deep part of the canyon, how long would it take to hit the bottom? How fast will it be going? So, unlike what we've been doing for the past couple of days, we're used to VI, VF, A, T, and D in the X and the Y. But in this case, we're just dropping it, so there's nothing going on in the X dimension. I was just trying to help you remember how we deal with one-dimensional kinematics. So anyway, we know that the rock is going to be dropping a depth of 1,600 meters. We know the initial velocity is going to be 0. We're looking for the final velocity. We know the acceleration is negative 9.8, and we're looking for the time. So VI, VF, A, T, D, I think the best equation to be using is going to be D equals VIT plus 1/2 AT squared. So negative 1,600 equals 0 times T, which is still going to be 0, plus 1/2 of negative 9.8 is going to be negative 4.9 T squared. We can clean this up and just make it negative 1,600 equals negative 4.9 T squared. We can do that out on that calculator, divided by negative 4.9. So 326.5 equals T squared. We don't want T squared, we want T, so we'll take the square root of both sides. And that should be about 18 seconds. So that's how long it's going to take to fall, is 18 seconds. And then how fast will it be going? We want the final velocity. And I would say the best way to do that is going to be VF equals VI plus AT. So VF is what we're looking for, equals 0 plus negative 9.8 times 18 seconds. So negative 9.8 times 18. That should be a VF of negative 176 meters per second. So there you go with that. 18 seconds and negative 176 meters per second. Next, the Empire State Building is 381 meters tall. If I throw a penny off of it with an initial velocity in the X dimension of 9 meters per second, how far in the X dimension will it land? How long will it take to get there? So you know what? I'm going to pause this quickly, and all I'm going to do is just make charts for VI, VF, ATD. Sorry about that. So I just wanted to make life easy for myself and make the X, Y, VI, VF, ATD chart for all of the problems, so I didn't waste a ton of time. So as you can see, I just did that. Okay, so the Empire State Building is 381 meters tall. If I were to throw a penny off of it with initial velocity in the X dimension of 9 meters per second, how far away in the X dimension will it land? And how long will it take to get there? So as we know, I'm asking you for the time, but we always need the time. So let's solve that first. Let's start with what we know, and then we'll solve for time, and then we'll solve for distance in the X. So we know the acceleration in the X dimension is 0, and in the Y dimension is negative 9.8 because we're dealing with a projectile. This is a cliff problem. So here's the Empire State Building, and we're throwing a penny horizontally, as best as that can be horizontally, off of it with initial velocity. So the Y initial velocity is going to be 0. The X is going to be 9 meters per second. We also know the final velocity in the X is going to be 9. Time is what we have to find. We know the penny is going to drop, grand total of 381 meters. We also want to know how far away it's going to land in the X dimension. So I hope that makes sense, at least in terms of what we're doing and where we got all that information from. Now it's just time to solve. So to find time, I got a VI, an A, a T, and a D. Well, at least I've got the VI, the A, and the D, and I'm looking for the T, so I would say the best equation to use is going to be D equals VIT plus 1/2 AT squared. So negative 381 equals 0 plus negative 4.9 T squared. -381, just like we did last time, divided by -4.9. It's going to be 77.75 equals t squared, because I just divided both sides by -4.9. We don't want t squared, we want t, so we're going to take the square root. T is going to be the square root of 77. Square root of 77.75. 8.81 seconds. 8.81 seconds. All right, so that's how long it's going to take to fall. And then because we're looking for displacement in the x, we're going to do v equals d over t. V in the x is 9, d is what we're looking for, and time is going to be 8.81 seconds. So we can just cross multiply 9 times 8.81 equals d times 1, which is just d. So we are going to, so it's just going to be 9 times 8.81, which is going to be 79.29 meters away. That's where it's going to land. 79.29 meters away. All right, so I hope that made sense and we got that. David Beckham kicked a soccer ball with an initial velocity of 25 meters per second. If he kicks at an angle of 44 degrees above the horizon, how far can it go? How long can it stay up in the air? So this is now a launch problem. So here's the soccer field. The ball's going to get launched from the ground and land back on the ground, and we want to know how far that is. And we want to know how long can it stay up in the air. So we're also looking for the time. Okay, so we know the initial velocity is 25 meters per second. However, that doesn't go in VI. That is neither VI in the x or VI in the y, because that is 25 meters per second in both. In other words, part of that 25 is going in the x, part of that 25 is going in the y. So we have to do a little bit of trig to figure this out, and I'm going to try and make a slightly cleaner triangle for us here. So this is 25. And this is the velocity in the x, and this is going to represent the velocity in the y. Such a nice triangle, huh? So that's going to be v in the x, and that's going to be v in the y. Now, we know the angle here is 44 degrees. So what we're going to do is we're going to use trig, little sine, cosine, and tangent action, to figure out the y and the x. So the x, we have the hypotenuse, so I'm going to say cosine is the one we're going to use. Cosine of 44 equals adjacent over the hypotenuse, but the hypotenuse is just 25. And then for this one, it's going to be sine 44 equals the opposite over 25. And all we're going to do to both of these, remember that sine 44 and cosine 44 are just numbers. So I'm just going to multiply, literally cross multiply. 1 times O is O. 25 times sine 44 times 25. 25 sine 44. 17.36. So O is 17.3. 17.36. Around right. So all I do is multiply 25 times sine 44 equals 1 times O. So O is 17.36. And then for this one, cosine 44, 25 times cosine 44 is 17.98. And that's 1 times A. So A is 17.98. And here's the first question I guess I want to ask you. These are pretty close to being the same thing. And that shouldn't surprise you because 44 degrees is almost 45 degrees. And if this is a 45 degree angle here, that means this side and this side have to be the same. So that's just a little other kind of check for you to see if you got numbers that are in the remote zip code of possibilities. But regardless, O and A, these are your two initial velocities. So the O is the VI and the Y, which is going to be 17.36, and the VI and the X is going to be 17.98. And because we know there's no acceleration in the X, 17.98 is how fast it's going when it comes back down. And in the Y, it's vertical is because it starts and stops at the ground. This is going to be negative 17.36. And that's one of the rules that we had a couple weeks ago, if you remember when I gave you the rule for dealing with two-dimensional projectiles. So the next piece of this that we also know is that my y acceleration is negative 9.8. We got to figure out the time. We know the distance in the y is going to be 0 because it started on the ground and ends at the ground. And we're going to have to figure out the displacement in the x. So now, I think the easiest thing to find time is VF in the y equals VI in the y plus AT. Because we have pretty much everything. VF is going to be negative 17.36. VI is positive 17.36 plus negative 9.8 T. So let's do a little bit of math. We're going to subtract 17.36 from both sides. So 17.36, divide that by negative 9.8. That's going to give us a time of 3.54 seconds. 3.54 seconds. I hope you got that too. Again, negative 17.36 minus 17.36 is going to be negative 34.72. Divide both sides by negative 9.8, and you should get 3.54 seconds as your time. Now that I've got that, I can go ahead and we can use V equals d over t to figure out what the displacement is in the x dimension. The V in the x is 17.98. D is what we're looking for. Time is 3.54 seconds. So just cross multiply 3.54 equals 1D. I'm sorry, 3.54 times 17.8, or 17.98, 3.54 times 17.98. It's going to be 63.64. 63.64, and that equals 1D, which is just D in the x. Okay, so I hope that made sense. We're a little more than halfway done. Yay. During Swan Lake, a ballerina jumps into a pirouette at an angle of 39 degrees and initial velocity of 3 meters per second. How much time does she spend in the air? How far away does she land? This is exactly the same as the David Beckham problem we just did. So this time I'm going to start with our hypotenuse. We know that is 3 meters per second, and we're jumping 39 degrees. And we have to then solve for what's going on in the x dimension and what's going on in the y dimension. A little cleaner of a y. That looks better. So in order to figure this out, again, cosine 39 equals the adjacent over the hypotenuse, which is 3, and sine 39 equals the opposite over the hypotenuse, which is 3. And to figure this out, 3 cosine 39 is going to be 2.33 meters per second in the x, and 3 sine 39 is going to be 1.88 meters per second in the y. So 1.88, 2.33 stays as 2.33 because there's no acceleration in the x. But in the y we have negative 9.8, and she's going to land back on the floor. So that's going to be negative 1.88 when she comes back down. I hope you're okay with that, because it doesn't say in the problem that she lands anywhere else. I would have to tell you, I mean, you can make an assumption that a ballerina is going to jump from the floor and land back on the floor. Unless I said she jumped off a table and then landed on the floor, or jumped from the floor onto a table. I mean, I'm not a dance team person, so I'm not quite sure how that works. But for our sake, she starts on the floor and ends on the floor. Again, we're going to spend some time looking at time, and then we want to know how far away she lands, because we know the final displacement in the y is going to be 0. She starts on the floor and ends on the floor. So again, I think the easiest thing to do is going to be VF in the y equals VI plus AT. VF is going to be negative 1.88. VI is positive 1.88 equals negative 9.8 T. Sorry, plus negative 9.8 T. So negative 1.88 minus 1.88 gives us negative 3.76 equals negative 9.8 T. Divide both sides by negative 9.8. We should get a time of 0.383 seconds. So I'm just going to leave it as 0.38 seconds. And now V equals D over T in the X is going to be 2.33 equals D over 0.38 seconds. 2.33 times 0.38. I'm just cross multiplying again. 2.33 times 0.38 equals D times 1. We should get 0.8854 meters away. Okay, so I hope that helped. Hope that made a little bit of sense. Now we have an interesting one. An airplane is flying at a speed of 200 kilometers an hour, flying at an altitude of 8,000 meters. How far away will a bomb release at the ground? How long will it take to reach the ground? So now we've got a plane flying. This is my plane, and it's releasing a bomb. And we know it's flying at a height of 8,000 meters. And we know the plane is flying 200 kilometers per hour. And so there we go. Now we can start with this. The issue that we have to deal with first before we do anything else is we have a distance here that's meters and we have a speed here that's kilometers per hour. So we need to get out of kilometers per hour and into meters per second before we can actually go ahead and plug anything in. And if you didn't do that, I hope that you understand you have to. So let's set up some train tracks. 200 kilometers per 1 hour times, let's see, kilometers on the, I'm going to get rid of kilometers first. So 1 kilometer on bottom, that's going to cancel that out. 1,000 meters. So now I'll be in meters, which is good. 1 hour on top. 60 minutes, and then 1 minute over 60 seconds. So this will give me hours will cancel, minutes will cancel, I'll be in seconds, and kilometers will cancel, I'll be in meters. So now all I have to do is 200 times 1,000 times 1 times 1 divided by 60 times 60, which is 3,600. So divided by 3,600. That's going to be a speed of the plane of 55.55 meters per second. And that can go over there. So the plane is flying horizontally at 55.5 meters per second. Therefore, the bomb is also going 55.5 meters per second because of our rules. No acceleration in the x dimension. The bomb is going to drop from rest in the y. We don't care how fast it's going, we just care about how far it's going. But we could figure out VF if we wanted to, but we really care about that. We know it's also going to fall 8,000 meters. So I hope the setup of this makes sense, and the snarky part was coming up with that conversion from 200 kilometers an hour to 55.55 meters per second. The acceleration here is negative 9.8. So VIAT is what we're looking for in D. I'm going to say again, D equals VIT plus 1/2 AT squared. Negative 8,000 equals 0 plus negative 4.9 T squared. Just to clean this up, it'll be negative 8,000 divided by negative 4.9. That will be 1632 equals T squared. And then we don't want T squared, we want T, so we'll take the square root of both sides. Square root of that thing, square root of that thing. T will be 40.4 seconds. So 40.4 seconds. And now we can do V equals D over T for the X. So 55.5 equals D over 40.4 seconds. Cross multiply. 40.4 times 55.5 equals 1D, which is D. So our distance in the y will be 2,242 meters away. Hope that made sense. Now, one data point for the potato cannon. This bazooka was 8.5 seconds total in the air at an angle of 30 degrees. So now we're figuring out how far away it's going to land, what its maximum height is going to be. This is a weird problem because I don't give you the initial velocity. We have to kind of be ingenuitive to figure out what's actually going on. This is actually going to take a little bit of time. So here's what I can do. I can make a triangle because we've done that a lot anyway. So we'll start with a triangle. And we know the angle of the triangle is 30 degrees. How far away it will land? What will its maximum height be? Fine. So we want to find d in the x, and we want to know its maximum height. So we're actually going to go for d in the y. And I hope you understand that its maximum height is actually going to happen not at 8.5 seconds, but at 4.25 seconds. So everything we're doing here, we're going to have to figure out at 4.25 seconds. And the interesting part here is once we have that for half of the height, well, I'm going to know half of the total distance too. Or not half the height, for the entire height. If I know how high it went at 4.25 seconds, I also know how far it went. I can figure that out. But that's only half the trip, and you can assume that the potato or the projectile will finish its trip by going that twice. So we'll come back to that, but like we're going to end up multiplying this d by 2 at the very end. And that's really it. We don't know anything else. So we need to figure out the vi in both the x and the y. We know the vf and the y is 0. And we know the acceleration is negative 9.8. We also know the acceleration there is 0. So at this point, I've got a vi, a vf, an a, and a t. I can use vf equals vi plus at to figure out what's going on with this launch, and I can at least figure out what this initial velocity is, and we'll see if that can help us. So my vf in the y is 0. Vi is, I have no idea, negative 9.8, and t is 4.25. So let's do a little bit of math. Negative 9.8 times 4.25 is going to be negative 41.65. So 0 equals vi plus negative 41.65. And I'm going to have to add that to both sides, and vi will be a positive 41.65. Now that's kind of cool. And I hope you understand why that's kind of cool, because all we did was we knew the hang time, and we were able to figure out how fast it was going in the y dimension. So that's nice, 41.65. And once upon a time, we learned about triangles, and if you have any side and an angle, you should be able to figure out the other side. So in this case, I have, if this is my starting angle, this is the opposite, this is the adjacent. So I have the opposite, I want the adjacent, I can use tangent of 30 equals the opposite over the adjacent. But I already have the opposite. The opposite is 41.65. So now what I can do is I multiply both sides by a. Okay, so a tan 30 equals 41.65. And then I'll divide both sides by whatever tan 30 is, because that's just a number. 30. And I'll have a equals, let's see, 41.65. 41.65 divided by parentheses. Probably want to do that. Tan 30, close the parentheses. 73.13. So my adjacent is 73.1 meters per second. So now I'm in business, because now this is exactly what I usually have. 73.1 meters per second. This is what I usually have when I have a two-dimensional projectile. I have the vi in the x and the y, and I have some other information. So at this point, I guess I want to know how high the thing goes. So let's do that. I got a VI, VF, A, T, and a D. So I guess we do D equals VIT plus 1/2 AT squared. That's fine. So D, which we don't know, equals 41.65 times T, which is 4 1/4, plus 1/2, negative 9.8, 4 1/4 squared. So let's see, 41.65 times 4 1/4 is 177.01 plus 0.5 times negative 9.8 times 4.25 squared, close the parentheses, minus 88.5, so 177, I'm going to call that, I'm leaving that, 177 minus 88.5 should be 88.5 meters high. So that's how high it goes. And then how far does it go? I can do V equals D over T again. V equals D over T for the X. So 73.1 equals D, which I don't know, over 4.25 seconds. Cross multiply 4.25 times 73.1. That is 310.675 meters. But we're not done. This is all about the first half of the trip. What about the second half of the trip? Remember, this height is 88.5. This height, according to the calculation, is 310. What about this? Not height, sorry. This distance is 310. What about this distance? That's also 310. So we multiply it by 2, and we should get a distance of, I'm going to bring it down here, 621.35 meters. Okay, so I hope that makes sense. Or you could just multiply the time times 2. So 4 1/4 times 2 is 8.5 seconds, which is the real time, times 73.1. And that should again give you 621.35 meters. Okay, so I hope that made sense. And this is an A problem. This is definitely an A problem because I didn't give you much of anything except time and an angle. But it's up to you to realize you can figure out this initial velocity, and then you can use some trig to figure out that initial velocity. And once you have those two things, you're in business. So I hope that made sense. And let's go on to the last one. Plane that is heading, this is going to be, I like ending on a nice easy note. This is just a riverboat problem, even though it's not a river, it's an airplane. Plane heading north at 150 meters per second. So north at 150. Experiences a wind blowing east at 20 meters per second. Not to scale. So east, draw a vector diagram, find the resultant velocity. So we're starting here. We are ending up going north and then east. So we want the resultant velocity. So we want that as well as, because we're asking for velocity, we also want the direction. So we want the angle too. So it'll give us theta equals I don't know, and VF I don't know either. So VI is going to be in the y dimension 150, and it's going to keep going 150, and the x dimension is going to start as 20 and end as 20 because in neither case here we're not dealing with a true projectile. The acceleration is 0. Time and displacement don't matter because we're not really asking you that. We just want that displacement, or I'm sorry, that final velocity. So we got 2/3 of a right triangle. I'm going to do Pythagorean here. 150 squared plus 20 squared equals 22,900. And then we take the square root of 22,900. 22,900. We should get 151.32 meters per second. And then, so that is our final velocity, which is there, which is neither the x or the y, it's a combination of both. And for our angle, I would say we're going to do inverse tangent because we have the two sides, so we're going to go backwards. Inverse tangent, opposite over adjacent, 20 over 150, because this is the opposite side of this angle, this is adjacent to this angle. Second and 20 divided by 150. So that will be a theta of 7.59 degrees east of north. We went north first, and then we turned and went east, so we're going 7.59 degrees east of north. Okay, I hope that helped, and we'll round this up tomorrow, and you can ask me any questions you have, and hopefully I'll be able to give you another problem set to work on for, well, I'll give you another solution set tomorrow, or I'll give you another problem set tomorrow. You can work on it for Wednesday, but I don't see you on Wednesday, so I will upload another solution set, and we can deal with it on Thursday before the exam. Okay, hope this helped.